Hello everyone, I would like to extend you a warm welcome to my video, where we will be creating a symbolic differentiation program in Python from scratch. I think coding is up an algorithm to solve a math problem is a great way to get a deep understanding of that problem. Symbolic differentiation in Python from scratch. In this video, I will live code up the whole program and explain interesting math and coding stuff behind what I do. For prerequisites, basic coding knowledge helps, as well as an understanding of what a derivative is. Our end goal is to be able to derive expressions like this, something like 4x squared plus x plus -2. End goal, derive this to get something like this. Eight x plus 1. The program will be interactive, have tests, and I'll link the code in the description so you can hack away various improvements or solve the challenges I mentioned in this video. Let's start with just numbers, variables, and addition. So if we get something for our input like x plus 4, how do we go about turning this into something the computer can understand? Well, we're going to want to parse this into something that the computer can use. Right now, the plus is in the middle of 4 and the x, so it is in something known as infix notation. We want it in prefix notation because that'll be easier to parse. So we want to turn this into something like plus x 4. Let's do just that. So we're going to define a parse function. It's going to take in an input string as text, and well, let's add some tests. Parses an input formula to derive. And if we parse something like x plus 4, we want to get back plus x 4. Well, what happens if we parse something like just x? Well, we just get back x. We parse a number. We just get back that number. And we can have other variables too. If we parse y plus x plus c, then we want something like plus x, start with y, plus x, z. Right, let's make just that. So how are we going to parse this input formula to derive? Well, we're going to have to write some Python code. Starting us off, we can check if the formula that's passed in is a variable. So let's go ahead and try to parse what's given. Parse as a variable our input text. And if that isn't none, we'll return that very x. Great. We have this function call. Now let's write it. So what is that going to look like? Well, that's going to look like a function that takes in, again, some text and parses a variable from it. And for us, variables are going to be one letter lowercase English letters. So for example, parse variable something like x. We'll just return x. parse variable of y. We'll just return y. And let me try to use single quotes, and you'll see y in a second. And then something like parse variable, a number, will return none, and parse variable x plus 4 will also return none. We can already run our tests using the Python doc test module. So I'm using Python 3.8 here. You can use any Python version with the doc test module. So -m doc test and then name the file. And it'll run the doc test, and you can see that we failed a bunch of tests in both parse and parse variable. Let's do the parse variable ones. Checks if text is a single lowercase English letter. So we could do something like if text in A, B, C, D, E, F, G, H, I, J, K, L, M, P, Q, R, S, T, U, V, W, X, Y, W, X, Y, and Z. Well, then we need to return text. Otherwise, we return none. If you don't write a return in Python statement, it automatically returns none. And we can see that if we were in our tests, we've had a bunch of successes. We did have one more fail in this. Oh, it's accidentally wrote none instead of just leaving it blank. Now, okay, all our tests in parse variable have passed. Let's move on to parsing the next thing. Like, let's start parsing numbers. Nice. Now let's take care of numbers. Numbers are a little more complicated, especially because we're going to want to handle both integers as well as decimals. So in this case, and returns it if so. Let's write some tests first off. In these triple quotes at the beginning of a function, this is called its doc string, and you can add some doc tests. So we're gonna write something like 1. That's 1. If we get something like -2.5, well, that's -2.5. And if we get something like 0.0 or just 0.0, that's just 0.0. And again, we want to add a test where let's something like x plus 4, we return none. So we're going to leave that empty. Again, I do want to use single quotes for consistency here. Okay, nice. And how are we going to do that? Well, let's write a helper function that checks if a character is a number. We can just return that if that character is in 1 through 9, including 0. And we're going to check if a number is negative. How do we tell if the number is negative? Well, if it has a preceding negative sign. If negative equals text at 0, well, we set negative to true, and we can move text forward. Nice. Now that we've taken care of the negative case, we want to check if every letter in the string is an actual number digit, and we could do that with just mapping char is number over everything in text. And if those are all true, then we know we're at an integer. Specifically, at this point, we can check if it's negative. We can return -1 times int of text, and this is just turn an actual integer into an integer, and we can return that. Else we can return just int of text. At this point, we should have some tests passing. Nice, 2 over tests pass in parse failure or parse number, and then the ones that don't are the ones that can concern themselves with decimals. Okay. Okay, so at this point, we reach this bit of the code if we're not an integer, and we can transform the text again into something where we replace just one period. This is what the one here means with nothing. So delete one of the first occurrence of a period. And then now we could do a similar check. Char is number text. Then if it's negative, we can return a float. Else we return, or a negative float, else we return just the regular float. And then if we run our code, we have a couple of failures. So let's see. Oh, I want to use text no period here. No period. That's our test to catch little mistakes, and wonderful. All of our tests in parse number pass, and then we have a few tests in parse text that fail up. And then one thing I noticed is we get an exception for parse of 5.6. That's because I accidentally passed in the float here instead of a string. Nice, expected 5.6. And then now let's actually call this similar to how we call parse variable. We can call parse number. And we'll see if that works. Yep. Now let's do next case where we parse plus of text. That doesn't equal none. We return x. Okay, what is parse plus going to look like? Parse plus. Let's add a few quick tests, starting with the case x plus 4. We want that to be plus x4 parse plus x plus y plus z. We can copy it from here. And then let's have a negative case. Well, what happens if we parse, I don't know, x plus 2? This should fail. Okay, now how do we do this? Well, we will check if we have at least one plus symbol. We'll split the text on that, and then we'll recursively call parse on the left and the right side. So we'll have some recursion coming in, and that'll be helpful for cases like this where there's more than one plus. So starting, we're going to check for the plus character to make sure we have at least one of them. If we have at least one of them, we can split text on the first occurrence of plus and only split once. The reason we only want to split once is we have something like x plus y plus z. We want to kind of split this into x and then y plus z. and then recursively call parse on both sides, because parse can take care of y plus c. And then we'll get the left and the right side by calling parse again. Split 0, parse split 1, and you can return. Oh, now we want to check, okay, if those correctly parse into whatever, so as long as they're not none, we can return plus left, right. Okay. And then we want to be able to parse things with and without spaces. So let's run the tests. In parse plus, we pass our first test case without the spaces. We fail our second test case. That's because we don't deal with spaces at any point, and our code above knows how to parse just X, doesn't really know how to parse X space. There's a really easy fix for that. We can just remove all spaces at the very beginning. Text equals text dot replace spaces with nothing. Here I don't pass in the count because I want all spaces to be replaced. Nice. And here we seem to parse things correctly. Let's look at this case. Okay. So in this case, it gets parsed into X, Y, Z. And let's figure out what's going on with this other test case failure. Okay, X plus Y gets parsed into plus X plus nothing, 2. Not too sure what's going on here, so I'm going to add a print statements to help debug. Print text. Okay, so let's look at this parse plus x2 thing. X plus 2, X plus 2 plus 2. Okay, at some point, we're just getting an empty string for the thing on the left. So we want to make sure that if an empty string is the result of something that's passed in the parse, that's invalid. We don't accept empty strings, so we'll return none for that. So I think if I add if text equals empty string, return none, that might take care of our error if we delete our prints. Nice. Okay, if nothing outputs, that means all our doc tests have passed, including those for parse plus and parse. Now that we parse our expressions into easier for computers to use formats, we can start to derive. Let's do that next. All right, let's get to deriving. We have numbers, we have variables, and we have addition. Let's write a rule for deriving constants, deriving variables, and an addition derivation rule. Okay, let's derive. So let's start with deriving with an expression. Let's start with what happens if we get, okay, well, we'll get expression, so we'll get the output of parse. So we could get a number, 5.6, or any constant, and that'll derive to just 0. If we get a variable like x, well, we're deriving with respect to x. So derivation of expr with respect to x, or like also is dexpr over dx. Nice. And then, so for something like derive y, we would get 0. And derive, well, we get outputs of parse, so parse of x plus y, well, that would just be plus 1, 0. Eventually, we'll make sure this simplifies to 1. Okay, let's start by turning some of these into rules. Let's add some helper functions to check if something's a number and a variable. Let's define is int as a function that just checks if is instance of x is int. Do something similar for floats. And we probably want something similar to what we did up here for parse variable. I'm going to pull out is variable. Let's say is variable equals lambda that takes in x and returns x in this expression, and we can use is variable here. Cool. Now, okay, if is int expr or it's a float, well, then we just return 0. If is variable, and actually for the is variable, I also want to add a check that is instance x stir. If it's a variable, well, now is it x or is it not x? Well, if it's x and we derive with respect to x, we get 1, else we get 0. And finally, we have time for the addition rule. So if we're not a number, we're not a variable. That means we are something a bit more complicated. We are an expression. We can extract the operator, the left and the right from our expression, and we can check if the operator is plus. Then what do we do? Well, we return plus of the derivative applied to the left side and the derivative applied to the right side, because the derivative is a linear operator. Specifically, we can return derive of plus derive left, derive of right. Let's see what this looks like. We run our tests, they pass. This is all well and good, but wouldn't it be nice if we had a way to run this more interactively and specify any kind of regression we want and see the output? Let's do just that. Let's define a function where we ask, we parse, we derive, and then we print, and then we recurse. So let's ask first for some input from the user. Let's parse that. Parsed equals parse of x. Let's derive it. Derived equals derive of parsed. And what do we do after? We want to print. So let's print derived, and finally recurse. Nice. And let's see this in action. If main equals main, this is just check if we're invoking our script as a main function. Well, we run our dog test, but now we can run the whole thing like this and ask for that. Okay, let's try x plus y. Nice. X plus y plus x plus z. 4 plus x plus y plus 3.4 plus, I don't know, 4 million plus -5 plus y plus z. Cool. There are two improvements I see right off the bat. One is we want to be able to simplify our expressions, and two, sure, this plus with the list syntax data structure is good for computers, but it's not very human readable. So let's make a more human readable string. Let's start with the human readable thing by adding a new thing, this derive, and let's also evaluate before we print. Evaluated equals evaluate derived, and we'll print our evaluated. Okay, what will our evaluate function look like? Well, I'll just take our expression and turn it back into something that's human readable. So in our case, we want to turn an expression back into a human readable string. So if we evaluate x, we get x. If we evaluate plus x, y, we get x plus y. Okay, let's check if is int, if is x, if is int expr or is float expr. We just return that expression as a string, or actually if it's what do we want to do with numbers? If we get yeah, we want to return string of expr. If is variable expr, just return that expr. Now we know we're not at a number or a variable, so we can do the same trick we did before to get the things from our expression, and we can check, okay, if operator is plus, we can return what? Well, we want to evaluate, again, we want to recurse on the left side, and then we want to add that to evaluating recursing on the right side. Let's see this in action. Our function is called something new now, appdepper. Pretty good name if you ask me. Let's run our tests and let's run our code. X plus y plus z, 1 plus 0 plus 0. Looks good to me. Our program is coming along nicely, but one thing that stands out to me is when we derive x plus y plus z, we get 1 plus 0 plus 0. You and I both know that, well, if you add 0 to anything, you just get that anything back. Let's see if we can make a quality of life improvement so we simplify our expressions as we derive them. How do we do that? Well, we can actually update our derive code to have something like this, just result in 1, by making it so we simplify as we build our new expression. So specifically, instead of just creating a list, we're going to call a new function we're about to write, call it plus. And let's add some simplification rules to plus. Okay. Well, plus is going to take a left and a right, and we're going to want to simplify as we plus. So if we take something like x and y, well, we know that's just, or specifically, let's say x and x. Well, we know, or yeah, x and y is fine. X and y, we know that, well, that's just going to be plus x, y. What's more interesting is if we have something like x and 1, or x and 0. Well, that should just be x. And if we have something like 1 and 2, that should simplify to 3. Let's actually make these floats. And let's make this one negative. Okay, how to do that? Let's check that if left is 0 or left is 0's decimal, we just return right. And similarly, if right is 0 or the decimal 0, we return left. And if they're both ints, if is int left or is float left, and the same thing happens with right, then what do we want to do? Well, we want to return left plus right. Finally, we return plus left, right. Nice. And now if we run our tests, then run our program, we can see x plus y plus z gets simplified to 1. Awesome. Okay, we have our addition rule. We have numbers, variables, and addition taken care of. This is a pretty simple and boring automatic differentiator. Let's add the product rule and multiplication. So starting from the very top, we also want to parse multiplication. Okay, define parse multiply. Well, the format's going to be very similar. And so let's extract the common functionality and make it a more general solution. So if we parse mul x times 4, we get mul x 4. Let's just keep it a very simple test case. And let's define parse binary operator, the text, and the operator. We'll move all this code here. We also want to operator name. Okay, so if we notice that we have more than one operator, we want to split at that operator and return something, operator name. And now parse plus is just parse binary operator of text plus plus, and similar for binary mole, in case it's mole, bam, and let's add a case for parsing mole. And let's see what happens if we do, let's say, 4x plus negative 2z. Oops, let's see what this results in. Yeah, that looks right to me. We're adding 4 times x and negative 2 times c. Awesome. Let's paste that in. Okay, parse is done. We're gonna want to now derive, and then we're gonna want to evaluate. Okay, so if operator equals mole, what do we do? And this kind of shows you once you have a base thing built, it's really easy to add extra functionality on top of it. So let's implement the product rule. And okay, derivative of u times v is u dv plus v du with respect to x in this case. Both those derivatives with respect to x. Okay, so we're going to return plus. Okay, what are we adding together? Well, we're going to multiply, and we're going to need to add this multiply function of left derive right and mole right derive left. Let's close those up. We're gonna want to add the mole, but before we add the mole, I'm just gonna really quickly finish out evaluate. If operator equals mole, it's going to be very similar. We're going to evaluate the left, we're going to evaluate the right, and we're just going to have multiplication with no space to mirror the input we have above. Then we can add a test case for that. Mole xy, we want x times y. And then if we derive, let's see, 4 times x plus 3 times y, we should get 4. Cool. And let's add the rule now for plus, or for mole. Let's define mole, left to right. Okay, let's add some cases. So like above, okay, if we're multiplying 0 times anything, well, that's just 0. If we multiply 1 times anything, well, that's just the thing that 1 was multiplied by. And make this 1.0 just to practice. And then if we multiply 2 numbers, 3, 4.5, 4, and 2.5 to get 10. And something else. X and 2, well, that's just mole x2. Okay, let's turn that into code. Okay, if left is 0 or left is 0.0 or right is 0 or right is 0.0, holding 0. If left is 1 or 1.0, return right, because 1 is the identity element for multiplication, just like 0 is the identity element for addition. Okay, if right is 1 or right is 1.0, we return left. If they're both floats numbers, I'm just gonna snag this from here, left times right, and then finally we return mole of left right. Here's a little challenge: figure out how you can, similar to how we combine parse plus and parse mol above, how you can combine the functionality of plus and mol into some more generalized combination pattern with an identity element and some rules. Okay, now we have mol, we have derive, we have evaluate. Let's run our tests. They pass, and then let's run our symbolic differentiator. Plus 3 times y, get 4. Let's see what happens if we do something like 5 times x. 9. Oh, yep, that looks great. Cool. Nice. Now that we know how to derive multiplication, we can deal with things like x times x. Oops, I have a print left over from some off-screen debugging I was doing. Specifically, something really weird happens if you try to do x times x times x, or x cubed. Let me save this and rerun this. If I do x times x times x, I get back this, which x cubed, if we derive it, that's 3x squared. That's not what this is. Or is it? Actually, what's going on here when I figured out debugging my own is we're missing some parentheses and we're not simplifying. So if I wrap some parentheses to preserve the order of operations, well, now we can see that x times x times x is, well, x times x plus x times x times x, where there's parentheses wrapped around this x plus x, making it so this is x squared plus x squared plus x squared, or 3x squared. A potential improvement is this that you can add to derive or evaluate is to simplify things like this, where multiply through and so on and so forth. I'll leave that as a challenge for you to do at home. But now that we have our summation rule, let's add one of my favorite things, the power rule, as well as exponentiation to our symbolic differentiation program. So starting from the top, we're going to want to parse a new binary operator. We're going to want to parse exponentiation, or let's just call it pow for power. If we parse pow, something like 4x to the third, we should get pow, or multiply 4. Actually, in this case, let's just 4x to the third, we should get pow x3, and let's add return parse binary operator text exponentiation pow. It's a new case for parse pow, and let's add a more complicated case where we parse 3x to the fourth to get, well, let's see, we want to multiply 3 times the result of pow x4. And let's see if our tests pass. Nice, that looks good for parsing. And let's go on to deriving. Well, what is the power rule? Well, the power rule simply is if our operator is pow, well then what are we going to do? Okay, we're gonna multiply, we're going to bring the exponent down and then we'll subtract 1 from it. So we're going to return, we're going to want to multiply what? We're going to want to multiply a few things. So let me just write it here. D of x, let's see, just u to the n. Dx. What does that equal? That equals n times u to the n minus 1. All of that multiplied by du over dx. That way, if u isn't a function of x, that just results to 0. And if u is a function of x, we get the derivative, and that takes care of some nice cases for us. So we're gonna multiply. We're gonna want to multiply. In this case, our n is right. And we're gonna want to multiply that by pow of left to sub right 1. And we're going to want to have that whole thing multiplied by the derivative of left. Oops. 120 parentheses here. Nice. Yeah, now let's add a pow and a sub function. Subtraction is similar to addition. If we have something like x0, we just have x if we subtract 0 from something. And then if we have numbers, we can just have the number back. If right equals 0 or right equals 0.0, we return left. I'm not going to simplify something like sub 0x, since we don't have negative variables, just negative numbers, just like -1 times x. I could have this either be times -1x or sub 0x. I'm just going to leave it like this. You can change it if you want. And then, so something like if they're both ints, we just, if they're all numbers, we just subtract. Else we have sub, oops, lost my place there. And then for pow, we have some nice rules that we can help with our simplification. If we raise anything to the 1 or anything to the 0, that's just 1. Anything to the 1, that's just that anything. And then 0 raised to any power, we'll just have that always be 0. Unless the case, of course, is when we started with 0 to the power of 0, and by choice, I'm going to make that be 1. If right is 0 or 0.0, return 1. If right is 1 or 1.0, return left. If left is 0 or left is 0.0, return 0. I guess we could also have this be the case of or left equals 1 or left equals 1.0, because 1, I'll just leave it as it is. Else we return pow left, right. Okay, and finally for evaluate, we're going to want to operator equals pow return. I'm going to copy this to the power, and we're going to do something similar for subtraction. Sub. Just because I had a sub up there. Pass our doc tests, and let's try to derive something. Let's try to derive what we hope to derive. 4 times x squared plus x plus -2. Nice. 4 times 2x plus 1. That looks good to me. Yeah, I think that worked great. That we got what we wanted. Super solid automatic differentiator and a bunch of lines of code. Success. We can derive polynomials. Let's try something with some more variables, not just x. Let's see, x to the 5th plus 4 times x times y squared plus x times y times z, and let's see. Yeah, that looks right. That's 5x to the 4th, 4y squared plus y times z. Awesome. Yeah, I'm quite proud of how this turned out. We have a nice little differentiation program. Our end goal was to derive something like this to this. We did it. Let's clean up the code. Let's see, and let's talk about potential improvements. Thank you so much for sticking around, by the way, for the video. If you have any questions, please leave a comment and I'll try my best to answer it. And yeah, let me go through the code and mention some areas of improvements and some challenges for you to try at home. One thing I just noticed that I missed is I missed a G here, and there's something missing there. One thing that you might notice is in our parse code, we don't parse subtraction. That's because order of operations is kind of tricky to have addition, multiplication, division. So these are really good things to add, and you might want to rethink the parse logic, make it a little more robust, be a little more creative in how you parse to handle all those cases. Yeah, so subtraction, division. You might want to also add like trigonometric functions, so like cosine, sine, tangent, how to derive those, how to derive something like e to the x or a to the x. We only did the power rule for that. We didn't do things for exponentials. You might want to add other elementary functions to your symbolic differentiator, and then yeah, see what complicated stuff to do. Another improvement is we're always deriving with respect to x. You can modify this code so you can specify which variable you derive with respect to, and that could be really cool. Handle those cases. So yeah, those are some just ideas for improvements. If you have any other ideas of what can be improved, yeah, leave a comment, leave your ideas. Um, the code is all in the description. So if you do improve something, make a pull request on the GitHub with your username and like a folder, I'll have instructions there. And I'm happy to host your solution in that same repo with my solution. Subscribe to my YouTube channel if you like math or coding, and I plan to make more math and coding related videos. This is also my first video, so if you have any feedback on what went well, what I can improve on, I'd love to hear that from you. So yeah, leave a comment below and just have a great rest of your day. Bye, and I hope you had fun watching. I definitely know I had fun coding this up. See ya.